This is Chapter 7 on what are called normal distributions. So these are continuous distributions. Chapter 6 was all about discrete, and these are all about, Chapter 7 is all about continuous. So we're going to learn two types of continuous distributions. One is called uniform and one is normal. So suppose you have a friend that is always late. Maybe you are that friend, it happens. On any given day, let's say there's an equal chance of him or her being anywhere from 0 to 30 minutes late. So equal chance of anywhere from 0 to 30. Because each outcome is equally likely, it creates what's called a uniform distribution. That was one of our shapes that we studied, uniform, bell shape, skewed left and skewed right. So we're going to talk just a little bit about uniform distributions. It's just a small part of Chapter 7. So for uniform, let's try that again. For discrete, back in Chapter 6, random variables, we can calculate the probability for exact outcomes. So in Chapter 6, we were able to do probability of x exactly equaling 3. But for continuous random variables, we cannot calculate exact outcomes. Therefore, we calculate the probability of an interval of outcomes, or range of outcomes. So in a uniform distribution, we use a rectangle called a probability density function. And it's in the form of a graph. So we use what's called a probability density function in the form of a graph to calculate the probability of an interval of values. There are two conditions for a uniform probability distribution. The total area under the graph must be equal to 1. And again, it represents 100% of the data. Something we've been talking about for a while now. And the height of the graph must be greater than or equal to 0. And has a maximum height of 1 over the range. 1 over the range. And this range is referring to the range we studied back in Chapter 3. So Chapter 7 and Chapter 3 are very closely related. Chapter 7 is an extension of Chapter 3. So we use this graph to find various probabilities using the formula for the area of a rectangle. And we know the area of a rectangle is length times width. So uniform probability distributions make a rectangular shape. And so to find this area, it's the length here, which is anywhere from the start of the graph to the highest x value, times the height of the graph, which is 1 over the range. The range is the minimum and the maximum subtracted. So this distance is the range. That's your length. 1 over the range is your height. And if you multiply these two together, you get exactly 1. So length times width for the entire space is always going to equal 1 to represent 100% of the data. So one more note you might want to make is that the range is the maximum value minus the minimum value. So we're going to do an example of this using the scenario of your friend always being between 0 and 30 minutes late. So what is the probability that your friend will be between 10 and 20 minutes late? So we know the minimum in the range is 0 and the maximum is 30. If I subtract those two, 30 minus 0 gives me 30. and that is 1 over the range. It's not 1 over the max, it's the max minus the min, the range. So this distance is 30, this is 1 over 30 for a whole entire area of 1. So we want to know the probability that they're between 10 and 20 minutes late. So 10 is somewhere here, 20 is somewhere there. The length between 10 and 20 is 10, the difference between the two. The height is always 1 over the range. So 10 times 1 over 30, is 10 over 30, which reduces to 1/3, and as a decimal that's 0.33 or 33%. So there's a 33% chance that your friend is between 10 and 20 minutes late. That should visually make sense because the shaded region is 1/3 of the entire graph. So there's a 33% chance that they will be somewhere in that region. So these homework problems are pretty easy. You just have to know how to set them up, and it's a pretty easy calculation. Sometimes they ask you for the same information but in reverse. So on part B, it says it's 10 a.m. There's a 20% probability that your friend will arrive within the next X number of minutes. So this time they gave us the area. The probability is the area. Those are the synonymous. So if the area is 0.2, we know the height is 1 over 30. We're trying to figure out this width here from 0, calling 10 o'clock 0 when you're supposed to arrive, and this distance here represents the number of minutes it might take them to arrive. So we know that 0.20 equals 1 over 30 times x. Now there's a few different ways to solve for x. The way I think about this is that 0.20 equals x over 30. So you can always put the variable up top, and since the top is just 1, it becomes x over 30. And then to solve for x, we just multiply both sides by 30. So we're just trying to figure out what is 20% of 30. And I got x equals 6. So we're hoping that there's a 20% chance that your friend will arrive within the next 6 minutes. So that's working backwards. If they give you the area, which is the percentage, if they give you that value, you always convert percentage to decimal. That is your area, which is length times width. You always know the height, but you're trying to figure out the distance here. And you just work backwards with a little algebra to get there. Excuse me. All right, so that's uniform distributions. You'll have a couple homework questions and maybe one test question over uniform distributions. If you see the word uniform, that's what you're looking for. So we're looking for the word uniform, and that's when we know to draw the rectangle. All right, moving on to what are called normal curves. We've actually studied these back in chapter 3. We're just going to look at them again. So a normal curve, which we've been calling a bell curve, is another continuous distribution shape that we're going to study. So uniform and normal are the two shapes we're going to study. Normal and bell curve are synonymous, those mean the same thing. And so a normal curve or a bell curve is used to represent continuous random variables that are said to be normally distributed. Normally distributed. This is also called a normal probability density function. The word density comes from calculus. We really don't need to know why it's called density, but calculus measures areas under curves, and so that's considered a density of the curve. So normal probability density function is another phrase you might see. We're first focused on the word normal. So normal curves or bell curves have some special features. One of those special features is called an inflection point. So normal curves have what are called inflection points. And these happen at mu plus 1 sigma and mu minus 1 sigma. So 1 standard deviation away from the mean. So what happens is we have our mean in the center if we're looking at figure 4. If we go 1 standard deviation above the mean and 1 standard deviation below the mean, the curve changes what's called concavity, which is again a calculus term. You just need to know that that concavity change happens at 1 standard deviation. So if you think about a roller coaster, the first half of the fall on a roller coaster, it feels like you're falling and you're going to hit the ground. And that's when you're concave in or down. And then at some point on the roller coaster, you kind of catch and fall out of the drop. And that's when you're concave out. So this concaves in and this concaves out. And that change of concavity is called an inflection point. And that's, again, kind of hard to think about. You don't really need to fully understand it. You just need to know that it happens 1 standard deviation above the mean. And also on the other side, it goes from concave down to concave up or out. And that's the other inflection point. So concavity is something you would study in a calculus class. We just need to know that it happens 1 standard deviation away. So this is when the concavity of the curve changes. Now when you draw a bell curve, it doesn't have to be this perfect. These are perfect little bell curves drawn with the computer. Our focus for statistics is more on the mean and standard deviation, which we've already seen back from chapter 3. So this should be mostly review for you. So the mean is always at the center of the distribution, and the standard deviation determines the width of the curve. All normal curves have an area equal to 1. Just like on the uniform distribution, that 1 represents 100% of the data. So the area is always equal to 1. Different standard deviations will change the width and height of the curve. Width and height. So we've kind of already seen this. If I have a distribution with a mean of 0 and a standard deviation of 1, it's centered at 0 and it goes 1, 2, 3. Back 1, and you could do it again, 2, 3. So that's mean of 0, standard deviation of 1. If I have a mean of 3 and a standard deviation of 1, it makes the same curve, it's just shifted a little to the right. So the mean just determines where the center of the curve is, and the standard deviation is the width. So two curves with different means and the same standard deviation look like the same curve, just shifted over. Standard deviation changes the height and the width of the curve. So these are both centered at 0, but the taller curve has a smaller standard deviation of 1, and the wider curve has a bigger standard deviation of 2. So if you have a wider standard deviation, the curve looks shorter because it can only cover that same amount of area. If I squish the standard deviation in, it makes the curve look taller and skinnier. It's kind of like thinking of someone who weighs 100 pounds. If someone weighs 100 pounds and they're short, they might look wider. If someone weighs 100 pounds and they're tall, they're going to look skinnier. And so it's that same concept. We only have 100% to work with, so I can either squish that 100% and make it tall and skinny, or I can stretch that 100% out and make it short and wide. But it's that same idea. So some properties of the normal curve, and you don't necessarily have to memorize all of these because we should already know most of these properties. The first one is that it's symmetric or symmetrical. about the mean. We studied that back in chapter 3. So we know everything's a mirror reflection from the mean. And because the mean, the median, and the mode are all just about exactly the same, the curve has a single peak at the highest point, which we report as the mean. So the mean is where the majority of the data are, right in that middle point. It has those inflection points we talked about at mu plus a sigma and mu minus a sigma. The area under the curve is 1, which represents 100% of the data. The area under the curve to the right of mu equals the area to the left of mu, which is 1/2, which we can write as 0.5 or 50%. So 50% is on each side of the mean. Property 6 is something we need to keep in mind for the rest of the course. As x increases and the graph approaches but never reaches the x-axis. And the same for decreases. So if you look up here, as my curve goes further and further out, it technically continues to positive infinity. It technically never gets all the way down to 0. So it's a limit, which again, calculus term, but it's an asymptote that just runs along the x-axis but never touches it. Same thing to the left. As it continues to get more and more negative, it approaches negative infinity, and it technically never touches the x-axis. For our class, we just need to remember that it continues forever to positive infinity, and it continues forever to negative infinity. Whether or not you understand limits and asymptotes, not important for this class. And then the last property is that the empirical rule is used, just like chapter 3. We're going to take it one step further and go beyond the empirical rule to really study different areas under the curve that are not exactly at one of the standard deviation points. Alright, so let's look at an example here. Trying to decide if the video is going to cut me off. I'm going to just set up this example and then I might have to start another video to continue it. So your textbook has raw data of the heights of 3-year-old females. I think it's 200 3-year-old girls. All the raw data is in your textbook, and they give you this nice histogram of all the relative frequencies for each one of the heights. The raw data have a mean of 38.72 and a standard deviation of 3.17. So if you look around 38.72, somewhere in here, you'll see that's where the peak of the data occur. And you can kind of smooth the curve over this data, roughly. And if we count by about 3, so if we go 1, 2, 3, 1, 2, 3, 1, 2, 3, so that's 1 sigma, 2 sigma, and 3 sigma to the right, you'll notice the data kind of fall off after 3. Same thing in the negative direction, 1, 2, 3, that's negative 1 sigma, 1, 2, 3. It's negative 2 sigma, and 1, 2, 3. The data just about fall off after 3 standard deviations. So for bell curves, wherever your center is, if you count 3 standard deviations in either direction, that's pretty much your entire distribution. And you'll see that with this set of data. So similar to a uniform distribution, sorry, lost my train of thought there. Similar to a uniform distribution, we use the area under the curve, just like we did for the rectangle. We found the area to calculate an interval. Well, we can say to calculate the probability of an interval of values. So different sections of the curve, we're going to be taking different probabilities, these calculations, and it's going to give us a probability of an interval of values. So because the normal curve is not a rectangle, we can't just do length times width because it's not a pretty rectangle. We have to use charts and the calculator to find our areas of different pieces of the curve. So in calculus, you learn how to get areas of the curve in different parts. For us, we're not going to learn how to do that by hand. We're going to learn how to read a chart where all the areas have already been decided, and how to use the calculator to get little portions of this curve because we're trying to find the area. So it's just like the uniform distributions, except we can't get the area ourselves. We have to rely on technology. I'm going to stop there so that the video doesn't cut me off, and in the next video we'll talk about example 4.